All right, so I'm going to make one more video on these types of problems. Um, this problem here is a trough. And so, yeah, let's go ahead and take a look at the solution for this one. We're going to go a little bit quicker on this one than we did on the previous problem. So if you haven't watched the previous video, watch that one. It was a square base pyramid, uh, and a little bit slower on that one. So it says a trough has ends shaped like isosceles triangles and has a length of 10 meters, width of 2 meters, and height of 5 meters, as shown in the image below. Water is being pumped into the trough at a rate of 7 cubic meters per minute. At what rate does the height of the water change when the water is 1 meter deep? Submit an exact answer. Okay, so let's go ahead and take a look then at step number one. What does step number one say? It says assign symbols to all variables involved in the problem and draw a figure if applicable. Okay, so the drawing is already taken care of us for us. Uh, so draw and then variables. So let's go ahead and talk about the variables for a little bit here. There's definitely a length. There is a width, a height, and then there's a volume, the volume of the water. Okay, so um, if water is being pumped in, right? So we have water that's getting pumped into this trough, then the volume is a function of time. Now, the height of the water, I'm going to just label it here on this picture, but the water, as water, increases, the height is going to increase as well. So the height is a function of time. The width is measured, there's two here, that's the width of the trough, but the width of the water, let's see, I'll mark it in red here. That's also going to increase as time goes on, right? The width of the water is a function of time. So we'll call it W of t. Now, one thing that does not change with respect to time is the length of, the shape that the water makes. Its length is always going to be, no matter what the height of the water is, the length is always going to be 10. Okay, so here the length L is not a function of time, it is a constant equal to 10 meters. Okay, so it's going to save us a little bit of time there to recognize that L is not a function of time. Um, it is just a constant. If we use it as a function of t, then it's just going to make our derivative more complicated. So we'll leave it as just L equals 10, a constant. Okay, um, so we've assigned variables. Okay, so let's go ahead and go to step two. State in terms of the variables the given information and the rate to be determined. Okay, so let's start with the rate to be determined. That's the question here. At what rate does the height of the water change? Okay, so uh, the rate of change of the height, we know that's called dH dt. We want to find this. When the water is 1 meter deep, when H equals 1 meter. Okay, what else are we given here? The dimensions of the container uh, are the length equals 10, the width of the container is 2, and the height of the container is 5. All of these are in meters. Now, these are the dimensions of the container, but they're not the dimensions of the water at any specific moment in time until this container is full. Once it is full, that they will be the dimensions of the water. But these dimensions here are mostly going to be used to try to find a relationship between the width of the water and the height of the water, as we saw in the previous video. And the other quantity that's given is dV dt. water is being pumped into the trough at a rate of 7 cubic meters per minute. The units there tell us that it's a volume divided by time. So dV dt is 7. So I'll put positive 7 cubic meters per minute. Okay, so we've written all the information and the rate to be determined. Step number 3 is to find an equation. So here, this is just a triangle. And so the area of the triangle is base, which actually they call it W here, W of t, base times height, H of t, uh, divided by 2, or, 1/2 width times height. And then we have to multiply to find the volume. We'll multiply then by the length of the trough. So our volume equation, V, is going to be equal to the area of the base, 1/2 W times H. I'm going to knock off the of T just to make our lives a little bit easier, times the length. Notice that this is very similar to the previous problem. It was the area of the base times the height of the object. In this case, the object, the height is now being called the length, but it's the same idea as before. Okay, so W is a function of time, H is a function of time, L is not. So we can actually immediately plug in 1/2 times W times H times 10. That quantity L is never going to change. So we can just plug in the length right now. It is 10, and this is in meters. So let's just keep that in mind. I don't want to stick too many units in here. And now we have we have V as a function of both W and H. But as we saw in the previous problem, we might be able to come up with some sort of relationship between W and H that will help us solve this problem a little bit more simply. So let's go ahead and take a look at a little cross section of this triangle, and it's a little lopsided here, but it'll do. The width, oops. So here's the water. The total width of the container we were given was 2 meters. The total height of the container we were told was 5 meters. And the triangle created by the water has width, we'll call this width W, because that changes with respect to time. And the height of this water we'll call H. And so as we mentioned in the previous video, let's see here. Actually, which one do we want to solve for? We want to solve for dH dt. So we want H to be in our equation so that when we take the derivative, it produces a dH dt. And that means we want to get rid of the W. So let's start by taking W and dividing it by H. The width of the water divided by the height of the water is going to be equal to the width of the container divided by the height of the container. And so now if we multiply by H on both sides, W can be replaced by 2/5 H. So let's go ahead and plug into our equation. V equals 1/2 times 2/5 H times H times 10. And we can see, hey, this works out pretty nicely. Where 2 times 5 is 10, so that cancels out with this 10. And so our equation is V equals 2H squared. Nice. We went from volume depending on L, W, and H to writing it only depending on H. So now we can take the derivative of both sides. The derivative of V is equal to the derivative of 2H squared. So we get dv dt equals, the derivative of 2h squared is 4h times, since h is really a function of time, this is a composition of functions, so we need to multiply by dh dt. All right. And then we can just divide both sides by 4h. And so we get dv dt, and let's see here, I'll write it, cancel there, we get dh dt equals dv dt divided by 4h. And so dv dt was positive 7 cubic meters per minute. For h, so for h was 1 meter. And notice that we're supposed to get, since dH dt is what we're trying to solve for, the units should end up coming out to meters per minute, right? But it looks like it might come out to meters squared. And that's because I got rid of a unit earlier. We said this 10 here had units of meters. So there is, when we combine the 10 with a 2/5 and the 1/2, we got a 2. This 2 has units of meters. So this 2 got multiplied by 2 and the derivative became a 4. So this has units of meters as well. So just to make sure that the units do work out the way that they're supposed to. So we get 7/4 meter, 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 meters per minute. Okay. So the height is increasing at a rate of 7/4 meters each minute when the height of the water is 1 meter. All right, so we went through that a little bit quicker. I'm not going to show the alternate solution in this case, but it would be if you're interested. It'd be very similar as the previous one, except you can even go as far as to consider L to be a function of time. And notice you'd have to use the product rule twice there. But just a little hint for anybody who does want to try this. When you take the derivative of L, you're going to get dL dt, which since L is a constant, how is the length changing? The length of the water is not changing. So that's going to be 0, and it'll end up canceling a few terms out. Okay, so I'm not going to spend the time to go through that. We talked yeah, I mean, this solution is good here. It's nice and short. Okay, so yeah, that is our answer, and I hope that helps out a little bit.